So we're going to get started. I'm Avani, for anybody that I haven't met. But we'll go around the room at the end and see what everybody's doing. So this is going to be just an introduction to not just unit testing, but actually like an entire testing workflow in R. Just telling Zach, this is also, I'm pretty new to implementing testing into my workflow. So if you have any advanced questions, we'll definitely get you to somebody who can answer them. But hopefully this will be about where everybody's coming in. So, all right, the first thing that I want to cover is this is not software testing. This is going to be unit testing or testing for us. So for graduate students, for people in the sciences, for people who are writing scientific code. And by itself, unit testing is a really simple concept, which you'll see in a couple of slides. But the concept of testing is really well developed in the software development world, and it's getting better developed in the scientific world. So what we're going to do is talk about different types of tests, and then I'll talk about what test-driven development is as a concept, and then we're going to talk about how you might integrate the concepts of test-driven development into your own scientific workflow. And then I'll give you an example with my own work. So just for the types of tests that you might see when you're doing a Google search for how to write a unit test, there's a bunch of different software development tests. The first that you might see is just a smoke test, which is just, does the program run? Does it do anything? That's, we're not going to talk much about the things that don't come into play that we're going to use. So smoke tests are more used in software development. Unit tests are programmatic tests. They're usually automated, and they evaluate a unit of your code at a low level. So that unit might be a function itself, or it could be a line within that function. And a lot of the tests that you're going to be writing to actually test whether your scientific code does the scientific thing that you want it to do, those aren't going to be unit tests in the strictest sense of the world. Strictest sense, they're just going to be more like functional tests, which are these. So functional tests are user-facing tests that, like we said, see if the code actually does what you want it to do. And those are the most important code, or the most important tests for scientific code, because you want to make sure that your results aren't erroneous in some way that you're not protecting. A regression test, you'll run into this a lot, especially in like Stack Overflow posts and things. These are tests to verify that the code that you previously developed and tested still works after you've changed it. So a regression test is a test that you write to fix a bug, basically, that you encountered in your code. All right, so now that you kind of know what the types of tests we're looking at are, we're going to talk about test-driven development just as a concept. And this is a suite of automated tests that specify the desired behavior of the program and verify that it's working correctly. So the goal is to have enough detailed tests to ensure that when all your tests pass, you feel genuinely confident that your code is running correctly. And the test-driven development workflow in software development is kind of categorized by this red-green refactor process. So red is you create a test and you conceive of code, or in our case data, that would fail that test. And then green, you make the code that you write pass that test by any means necessary. It doesn't have to be pretty code, just make it pass the test. And then you refactor. You look at the code you've written, you ask yourself if you can improve it, and then you run the test again after each code change to make sure that they still pass. And then if they don't pass, you're starting over with the red step. Not all of these practices are going to apply to our work. So what gets closer to scientific process is test-driven data analysis, so TDDA. And TDDA is sort of in an ideal world what we would do. And that's where you write the test first and then you write the code. And it's a pretty broad concept, and I put a link to a really good website that goes through TDDA as almost a philosophy up on the GitHub repo. So you should definitely, I encourage you to check that out on your own. But in general, it's a process that asks, has your data led you to make errors of interpretation when you get your results? So given the results, do you believe that your inputs were correct? How will your code then handle null values or missing values? Will outliers like extremely large or small values or invalid inputs like negative numbers invalidate the calculation you're trying to do? And if the values have dimensionality, like if your input is a data frame, do all the columns need to be at the same dimensions or in the same units? What happens when they're not? What does your code do, etc.? So in plain terms, every time you view an analytical result that you get from your code, you should be asking, why is this lying bastard lying to me? Which is really how to say, or how is this misleading data misleading me? And then writing the tests that will boost your confidence that you haven't been hoodwinked in the same way twice by your data. And that's the goal of the test that we're going to talk about for the most part today. But first we have to talk about stupidity-driven development. This is what's closer to what's actually going to happen on the ground. And Titus Brown, who's here at UC Davis, has this quote, for research purposes, we're much more worried about inaccurate research results than we are about crashing bugs, or bugs that crash our code. The latter are annoying and obtrusive, but they don't result in erroneous results. Inaccurate code causes much less visible problems that can be more serious scientifically. So we test the bejesus out of our scientific code while practicing a kind of long game with the rest of the code. We wait until there are actual behavioral problems that we can trace back to some bit of source code, and then we fix it. So this is the approach of stupidity-driven development. You're going to write the test for the obvious potential issues you can think of for your data. Then you're going to write the function and run your data through it. And then when you encounter bugs down the line as you work, you're going to write tests to fix those bugs that pop up, and then get on with more important things. So that's more of the boiled down stupidity-driven development workflow, but we're going to try to improve on it a little bit. So, but the priorities that you're doing with this workflow in order are correctness of your code, so making sure that you're getting the scientific result that you expect. Performance, you want to make sure it runs without having to leave for a week and coming back. User experience, not so high up on the list. And then last on the list is beautiful code. We're not that interested in beautiful, elegant code. Maybe you are, but at least for the first step, not yet. Okay, so you've thought about all these concepts, you've thought about all these test-driven approaches, and you have an analysis program that analysis that you're about to start, and you're ready to write some tests for it. Where are those tests going to live in your code? And I talked through this with Duncan Teppelang yesterday, and we kind of came up with this framework that you guys are going to have to tell me if it makes sense to you for your code writing. But basically, if a test needs to be run every time a certain function is called, the test should live in line with the code. It should live inside the actual function. And we'll call these runtime tests. If a test needs to be run just to make sure that you haven't broken the code after you've changed something, that test should live in its own test file and associated test data files in a separate directory. We'll call those test time tests. Yeah?
That's motivated by the computational time having to call the extra function, or is it just
I would say both. I haven't needed to run, I haven't had to write like complicated enough tests to where it's actually taking up a significant amount of processing power. So you would have to ask somebody who has written those tests to know what kind of directory structure they're using for their tests. This is kind of motivated for convenience and as a way for somebody who's really beginning testing, like for the first time ever writing a test. They're just like, where should that test go? Should it go in the function or should it live somewhere else? Yeah, I would say like, none of this really applies unless you're already at the functional programming stage. Like if you're just writing scripts for your analysis, most of your tests are going to be in line anyway with the script. Would you agree? Or?
Yeah, probably. Yeah, I guess I was kind of self-controlled.
Okay. Okay.
All other functions don't make it all made up.
Right. Okay. So that's a performance issue, and that should be. I mean, that's number 2 on priorities. So yeah, that's something that you're going to have to deal with for sure. And we can talk about specific use cases afterwards and actually maybe write some tests. All right. So runtime tests, they're these little, these actually are the unit tests of your code probably. So these are pre-automated. They make small assessments and either throw an error or a warning message. And oftentimes they make use of what's called an assert statement. And an assert statement is just a function that checks whether some condition is true or not. And if code is run that makes the condition untrue, the assert statement is going to throw an error. And the main function that R provides for assert statements is this function called stop if not, which is built on stop. But okay, so this is an example, but we're going to actually switch over to the script. So, all right, so within your script, you assign the value of 5 to x, and then you assign the value of x squared to y. And now I'm going to say stop if y isn't greater than 0. And right now, this shouldn't throw any errors, right? Because 5 is positive, x squared is going to be positive. So y should not be, y should not be less than 0. So it's going to run just fine. No error is going to be thrown. Now, if we introduce some complex numbers, that's going to make that condition untrue. So y is still x squared, but this stop if not is going to throw an error when we try to assign that value to y, or when we check if the value of y is valid. So that's just a really simple assert statement. Yeah. Yeah, I don't know how many of us are going to run into it, but I needed to make it untrue. All right, so this is going to be, so I've commented these out for this really simple function that I wrote to convert dimensions in pixels to millimeters. If we build that function, it's just going to take an input of width and height, and the resolution is set to a default of 300. And I want it to return the new width and height in the new dimensions, which are millimeters. So without the stop if not statements, the valid inputs are going to run just fine, and an invalid input, so I'm going to try to input a character value here. R is still going to throw an error because R doesn't like doing non-numeric arguments to binary operators and functions. So you're probably going to get an error. It's just not very informative if it's nested in a huge function. So assert statements can kind of help you make more informative error messages. So now if we add those stop if not statements and we try to run this again, it's now at least telling me that where it is in my, like what it is in my code that's throwing, that's not meeting the condition that I'm asking it to meet. We can make that even better. So stop if not is great. It's built in, no dependencies, anything. The assert that package and the assert R packages are even better for making informative errors out of assert statements. So assert that is one of the Hadley-Wickham packages, or the tidyverse packages, and it replaces stop if not, and it provides a number of user-friendly assert functions. And then I really like the package assert R as well. I actually just got introduced to it like yesterday. But it's great for error checking with your data. So if you're like me and most of my functions apply to actual data frames, the assert R package has some great functions to help you out with data quality checking. So now if we replace that stop if not statement that I did above with just the assert that function and the the assert that package, we'll run this. And now if we try to input the erroneous one, the error message is even more informative. So it used to be is numeric, height is not true. Now it's the argument height is not a numeric or integer vector. So you know exactly what the problem is with your inputs. So that's good. And then this is just an example of how the assert R package can be good for checking the quality of your data, or just some QA/QC before you even start your analysis. So a use case might be if you're reading in a data file that you know has more than 100 observations, but you want to make sure it imported all of them into R. So you're importing the right file or the file that you expected. So I just saved the cars data frame as a CSV in this working directory. I'm going to read that CSV, and now I'm asking, this is the pipeline from, if you guys aren't sure what the pipeline is, we can talk about that after the talk, but I'm asking it if I want it to verify that the number of rows in the data file that I just read in is greater than 100. And if it's not greater than 100, it's going to throw an error. So it does. Error in assert, verify, verification failed. And that error message isn't as helpful either, but as it could be, but it gets you started. And there's lots of options within those two packages to make your error messages more helpful. Okay, so let's go back to slides. Okay, so those are some examples of runtime tests. So those are the tests that you want to run every single time that you run that function. So it's user-facing. So you're trying to anticipate the errors that anybody else who wants to use this function, including future you, because I don't know about you guys, but future me in like 6 months doesn't know anything about the function that she wrote. So you're trying to anticipate the common errors that they might make. So are they going to forget that this is a numeric input, et cetera? Just help them catch those mistakes. All right, so test time tests are the ones that are more conceptual. So those are the ones that you ideally want to write before you even write your function, before you write your actual code. They're the ones that ask, what do I want my function to do? What should the output of my function actually be like? And that's kind of nebulous to give examples with. So I'm gonna try to do this with a concrete example. But these tests are going to live in their own test files. And I've found it pretty easy just because I've packaged up a couple of my functions that work with another data package. The test that package really helps, along with the DevTool package, to organize your tests in a sane way, and it provides some really convenience functions in RStudio that helps. But these are the tests that are only going to be run occasionally. Typically, they'll be run once when you first write the code, and then you'll run them again after you change any part of the code to make sure that your code is still passing all its tests up to that point. Okay, so thinking about how to write a test that answers those really broad, what do I want my output to be like, that's daunting. So we're going to make it pretty easy on yourself. So the first step is just to take a tiny sample of your data. 5 rows or observations is a good rule of thumb. You write your function on those 5 observations with them in mind, and you're trying, if you can, make those observations as representative as possible of the full data set. And then you write that function and see if it worked the way that you want it to for those observations. And the nice thing about the tiny handful is that you can actually just visually inspect the output. Did it do what you want it to do? And if it's what you expected to be, you've just written your first test. That is your first test. And now you can run the entire function on your whole data and see if you get any errors right away, or if it runs just fine and is silent. It's probably still wrong, but you don't know what's wrong about it yet. But you do at least have this test on the books, and you want to make sure, your goal is to make sure that your function always passes this first test at the very least, and then you can build tests on top of that. Okay, so then you're going to think of ways to trip it up. And some really canonized ones are just what happens if you feed it null values. Does it throw an error? Is it silent? Is the error intelligible? That's a good second test. If it fails, so if it can't handle null data, then you have to go back and change your code. And then you have to go back and run the first test and make sure that the change that you made to handle the null values hasn't broken or caused your first test to fail. So that's the workflow. It's just iterative, over and over and over again. And then, as scientists, you're just going to do your work, do your analysis, continue on, and then inevitably you're going to observe some weird behavior from your function that you didn't anticipate, or you're going to pass your function along to somebody else, and they're going to be like, I tried to run my data through it, and it gave me this weird thing. And so that's when you have to go back to the testing. You have to try to debug, which is a totally different topic, but you debug your code, and then you're going to write dummy data for that bug case. And you're going to change your code to address the bug so that your new dummy data test passes. And then you run all your other tests again, make sure you haven't broken anything with that dummy data, and rinse and repeat. So that's the testing process in the scientific context. Did that make any sense? Okay, and for anybody watching, if it didn't make any sense, hopefully this example will. So what's that? 5 people, awesome, okay. So we're going to go to, okay, so this, I'm just going to show a package that I'm developing. It's got a few nested functions, so maybe this will be a better example. for performance-oriented code. So I work with fish data, and I have a couple of packages that that are just convenience package. One of them is with all of my data, and the other one is the functions that I'm applying to that data. So first, I'm just going to load up my data package, and then so that you get a sense of what the data looks like. Yep. Okay, so the data is just each row is a detection of a fish. We've got the date and time of that detection, the receiver, the tag ID of the fish, the station, and some other metadata associated with it. And this function, fish paths, is just going to take my data frame, it splits it, it applies some grouping variables, and what it outputs is this data frame of the fish paths, so that I have a record of where each fish is at each station, and it's separated by some grouping criteria that I've specified. So the function works okay, and I know this because I've tested it on a little bit of dummy data. So this is my test file, and when you first have a package that you're trying to build tests for, the process is just load up DevTools. If you're using DevTools to develop your package, you'll load up, test that, and then you'll do use test. That is the function that will create the test directory for you. So I've already run that. So test that has built my test directory. It writes this script automatically that then will run every time you reload the package or test the package. And then your actual tests go in this test that directory, which is where we are now. So I've written a couple of tests around the subject of the correct number of columns in my data frame. So this was the first test. We loaded the packages that we needed. It's basically just an R script. Load the data, filter it to a subset, so a single fish. I want to make sure that it runs on a single fish first. And then here's the test. I just wanted to note that the original columns carried over into the new data frame that the fish tracker function creates. So we're going to expect that the number of columns of the data frame, the output data frame, is equal to 11. And we can talk about why this is a bad test later. But I just want to know that it added a couple of columns first. And when you run it, if nothing happens, it's good, it passed. And then we have a few tests here. But first, if we want to just see that all of the tests are passing, you're just going to do Command-Shift-T. And first, let me open this so you can see what happens. So DevTools is running the tests. It's loading everything, and it's going through that test directory. And all that tells you that your tests are passing is this little series of dots. So I have 4 tests in my test files, and I see 4 dots. And that means that all of the tests are passing. If they didn't pass, you would have numbers associated there, and then there's a process to help you debug those tests. Okay, so that was all great. The function was working fine. And then I realized that, and this is what happens to everybody, I'm sure, I realized that the code that I wrote originally for the function was really bad code. It just was ugly, and I could shorten it by literally 12 lines. So I went in, and just so that you can see what I did. Okay, so this was the original code. It had every single column spelled out explicitly, and I just realized that I could just save that typing by calling just the first row of that data frame. It also makes the function a lot more flexible, because now the inputs don't have to be this specific, and if I run it on data that didn't have it, then I wouldn't hit a weird length error, and so it would be better. Okay, so I changed the code, and I want to make sure that it's still passing all the tests. So change the code, and then go back into the function and run the tests. If it broke, which it did, you have to go back and change it again. And then, now that I know that I have added this flexibility, I want to see if that flexibility is actually working in the function. So I just wrote a new test that I want. So I'm now generating some sample data. So it's the same sample data as before, except that now I'm cutting out some of the columns. So dtrunc is just the same version of the data that it was before, but with a subset of the columns. So it only has 4 of the columns. And then create an object calling that function. The function seems to have run just fine, but I want to make sure that it did. So now I'm going to write a test that I'm expecting that the fish paths created from that first test should be identical to the fish paths created by my second test. Otherwise, I know the function is not doing what I want it to do. So run that, and that ran fine. So I formalize that as a test, rebuild the package, save it, commit it. And now I'm going to just keep working until I either figure out a better way to run the code, or I run it with new data and it's throwing me a new error. And then I'll run a new test. And that's it. Any questions?